So in this video, we're going to talk about the comparison test. I don't remember if I mentioned that most of the time we want to compare whatever series we have to a series that we know will converge or diverge, and which makes this series 1 over n to the p highly useful because we know exactly when this will converge. This will converge for p is greater than 1. And this will converge for will diverge for p is less than 1. So we don't usually compare to the geometric series, simply because the geometric series are a very special form of series, or are of a very special form in which we know it's the sum of the series. Whereas in the comparison test, we really just want to know whether a series converges or not. And a lot of times we're going to try to compare to something like the p-series, or that piece. I'm going to call it a p-series. If I'm wrong, I apologize. The p-series might be... No, that's the power series. Sorry, it's okay. So this is called the p-series. So, for example, if we know a series, so if we know an, and we know that it's bigger than sum of bn, bn. If we know that bn diverges, then a number, so if we know bn diverges, that means that in this particular case, we're going to let diverges mean increasing unbounded. If bn is, if the limit as n goes to infinity of the sequence of bn does not exist, that is not a particularly meaningful comparison, unfortunately. So in this particular case, we're going to say we know that the sum of bn is increasing unbounded. And if we know that bn is increasing unbounded and an is larger than something that's increasing unbounded, then obviously an has to also increase unbounded. So in this particular comparison, if we know, so if bn diverges, then sum of an will also diverge. Conversely, if you have sum of an is less than sum of bn, and you know that will converge, so bn will go to some finite number, then it means that an also has to be a finite number, because if an is an unbounded number, then it can never be less than a finite number. So we know that. Oh, yes, I always forget this one. But one of the conditions is that the terms of an have to all be greater than 0. So if a is less than 0, then we either have to multiply everything by -1 to produce a series in which all of its terms are positive, or you can't use the comparison test. And so in this particular case, if we know an is less than bn and they're both positive numbers, and we know that bn is some finite integer, therefore if sum of bn converges, then sum of an will also converge. So these are the two meaningful comparisons we make. Obviously, if we, for example, say we know here that an is greater than bn, and we know bn converges, then it's not a meaningful comparison, because an is larger than a finite number, but then we still don't know if this number that's this quote-unquote series, or this number that is larger than a finite number, is a finite number or if it just increases unbounded. And alternatively, if we know that an is less than bn and bn diverges, so bn increases unbounded, then we don't know if an is also increasing unbounded or if an just converges somewhere. So these are the two meaningful comparisons. Don't make not meaningful comparisons because they're not useful. And so we will do an example in which I will compare it to the p-series. For example, let's say you have 1 over the sum of from n equals to 1 of infinity of 1 plus the cube root of n. And so I don't know what this equals to, but I do know that the cube root, no, root 3, but the cube root of n is less than n, which means that the cube root of n plus n is less than n plus n, which means that 1 over the cube root of n plus n is greater than 1 over 2n. And so the other nuance that we should know is that since this statement holds for n greater than 1, it will hold for all numbers except for 1. So realistically, if we wanted to, we could reindex and say, well, n is 2, because if the series converges from 2 to infinity, then we just add one number to our finite sum, we still get a finite sum. So if the series converges for starting from any point, so starting from any index to infinity, then it'll converge for when it starts from all values to infinity, or given that all values is a finite value. So we know this holds for n is greater than 1, so we say, well, let's just start our index from 2 and check to see if it converges. We know this holds true, we know this holds true, and so we know this sentence holds true, which means that we can make the comparison of sum of n equals to 2 to infinity of 1 over n plus the cube root of is greater than the sum of n equals to 2 to infinity of half. So I can factor out a half times 1 over n. And since half is just a constant, we know that this is just equal to this half times the sum of n equals to 2 infinity of 1 over n. Again, because multiplication is a commutative property, it'll apply to each term of the series, and so you can alternatively just add all your terms together and then multiply. And we know this is a harmonic series, which means the series will diverge. Since the series diverges, these two series are equal, this series will diverge. Since the series is larger than a diverging sequence, than a diverging series, so this will diverge. We know that the larger series will also diverge. So the difficult part of the comparison test, or the relatively difficult part, is if the series we're looking for, what we think of as an, then the slightly more difficult part is picking the bn. For example, like how did I know to start with this comparison? And to be honest, it is trial and error and looking at it and inspecting and kind of thinking, well, what can I compare to this such that I will create a meaningful comparison, or a conclusive comparison rather. And a lot of the times we do want to compare it to some form of the p-series. So in this particular case, we did get a form of the p-series, and this one p is equal to 1, and so we know this would